So we're going to talk about machine learning and finance through the ages. What is CBRE? CBRE is a very large commercial real estate services company. We touch commercial real estate kind of throughout its entire life cycle, from funding to construction to managing. And we're very large, so I have to throw up a usual disclaimer. These are my opinions and no one else's, and certainly not the opinions of CBRE. So we've already talked about some really interesting motivating examples, and I want to try to move this talk pretty quickly, in part because it's warm, in part because I'm keeping you from the booze and the pizza. But we talked about some really interesting motivating examples, and I have not had a chance to talk to the other presenters. But we've talked about prediction based on a training set. What is this unlabeled object? This unlabeled object has 4 legs, is hairy. The chances that it is a cat, given it comes from the internet, is very high. So essentially, this is a probabilistic prediction. This is the logit, or variance thereof. We talked a bit about evaluation, which is a lot of what we do in economics. So we want to think about what is the effect of this drug on something. So one way to think about this is to randomize the unrandomized over a treatment. And we do a lot of this in economics. We call these randomized control trials. They've become very popular in development economics. Unfortunately, these things are rarely done in the United States or in Western Europe. They're typically done elsewhere. But you might want to ask the question, what's the impact of putting a healthcare clinic into a village? Or what's the impact of providing health insurance to individuals? So basically, you could think of, or what's the impact of this drug on a disease? So we have basic things that allow us to potentially randomize the unrandomized over a treatment. Oftentimes, these are not done in probabilistic ways. We don't think necessarily about this in a probabilistic framework, but we probably should. And, what's going on a lot here in Cambridge is basically having no model at all and a lot of data and deploying massive unsupervised learning techniques to look for patterns in genomic data to see whether there are disease clusters. So these are all really interesting ideas. They're really fascinating. And I'm going to talk about something really boring tonight, which is, given my risk appetite and my cash constraints, can I make some money? So that's basically what I want to talk about tonight. So let's start with 2 images, and I want you to look at these, and I want you to think about what these images might be. What data generating process gave rise to these images? So here's the first image. So I've kind of given you a little hint on the bottom. So I've said seconds. And this data generating process gives rise to a pattern. And we struggle and we look and we think, come on, I've got to be able to do something with this pattern. Whoop. So there's image 2. There's the second image, giving you a little hint again on the bottom. And again, there's got to be a pattern. I've got to be able to do something with this. Surely I've got to be able to do something with this. Well, here's the code that gave rise to the first image. This is non-deployable Python code that is a one-dimensional random walk. I stumble to the left or I stumble to the right. The second set of code is Apple share price in 2012. So let's go back. You laugh. You can take the code and run it yourself. I even set the seed for you. So there's image 1. That's the random walk. There's image 2. Apple share price in 2012. So I could pivot back and forth. Surely there's something going on here. Surely Apple's stock price in 2012 is not a random walk. So let's talk about a bit about the background of modern finance, which goes a long way back. We've given Nobel Prizes to some very, very famous people about this stuff, but this starts long ago. It starts under a Frenchman named Bachelier, who studied under Poincaré, who was another famous French mathematician who was working on chaos theory when there were no computers and there were no data, and well, the computers were people, but essentially there was no data. So Bachelier proposes that stock prices at the time were random walks, that everything you needed to know about a stock price today was contained in the price today, that looking to the past, absent other information, would never be that informative. You know, and it's not quite the correct framework, because stock prices are non-negative. They can't go below zero. You can lose all your money, but no one can come in and kind of take more money away from you. So we sort of changed it up over the generations, and we started to think about, rather than stock prices being a random walk, but price changes being a random walk, that returns were a random walk. So the percentage change in a price from yesterday to today is your return. That's the random walk. And so basically, as equity markets developed, individual stocks started to trade on exchanges. So you can think about the NASDAQ and tech stocks. And basically, a vast array of portfolios that emerged that included equities, bonds, and cash. And really, what came out of all of this stuff, and we are talking about a very long time, is just the basic principle that diversification is the key thing to investing. That it's really, really difficult to beat the market unless you're willing to take on a lot more risk than the market. And that's basically the key to modern finance. So this obviously is an interesting case for machine learning, for statistics, as we called it at the time. But data science requires a lot of things. One thing is it requires data. And data on prices are some of the oldest data that we have lying around. It used to be very, very infrequent, daily, going back hundreds of years. It would be quarterly, annual. But basically, data on prices are some of the oldest data series that we have. And they were originally pretty low frequency. You can now obtain tick data that basically exist in the range of a microsecond. So there can be a lot of data out there. So I talked about this, the talk was basically sort of a walk through machine learning and finance. So what was wave one? Wave one was standard theory and testing. So here's Apple's share price. When I teach this stuff in class, I usually have this series extend back to about 2002. What did Apple do in 2000? Setting aside the financial crisis, which is that downward blip, what did Apple do in 2007? There you go. Basically, they introduced the iPhone. That is why Apple is so valuable today. This is the exchange on which Apple trades. It's the NASDAQ. So think about price changes. We're going to look at how these things change over time relative to the benchmark on which Apple trades. So if I calculate the price changes and I just throw up a scatter plot, that's what they look like. And this is a classic model in empirical finance called the capital asset pricing model. So all I've done here is the axes are all the same. So it's minus 10% to 10%. Axes are the same. Basically, NASDAQ on the bottom, Apple there. So what do we do? What does one do with a scatter plot? Well, Gauss said fit a line to it. So we fit a line to it. And lo and behold, the line tells us a lot. That line tells us a lot. It looks like a 45-degree line. It looks like the identity. And that gets down to the core of what empirical finance is about, which is, can I do better through diversification or not? And looking at this line, it would be a little tough to say I can do better than diversification. So the original linear regression specifications for empirical finance was just regressing the log returns of Apple on the exchange on which it trades. It's the classic bivariate regression model. We all use different terms for this stuff. Economists say intercept and slope, and computer scientists say bias and this, that, and the other. But the point is, we can have a real-world interpretation of the regression coefficients from this sort of model. And this gave rise to something we call our arbitrage portfolio theory. Basically, the thing you want to think about is alpha is the thing that hedge funds claim they bring you. That's the bias term. That's what we call the non-diversifiable risk. If you can get a positive alpha on a portfolio, then that's something you want to think about investing in. So if we run this regression, again, using the standard package in Python, this is what we get. Now, I ran this a long time ago, but essentially what we see here is, and the underlying hypothesis behind this whole thing is that the intercept alpha is not different than 0. The slope coefficient, in this case NASDAQ, is not different than 1. So this is a basic idea in modern finance. So then, not being satisfied with this, we decided to get into prediction. So that was wave 2. And people said, surely neural networks will beat the crap out of linear regression in a framework. This has got to be true. So, and this goes back. I have a little poster. You can check it out on my GitHub page. I document kind of going back in empirical finance books the discussion of using neural networks, or using the terminology at the time as the terminology has evolved. But basically, every time they said, surely neural networks will do better than linear regression in this. Surely that's going to be true. So, working with a computer science colleague, I thought, well, surely it is true. So what we did was we basically took a basic linear model and the CAPM data that you saw there, and we fit a linear regression. We calculated average run times and average mean squared errors, standard 80-20 split, and the smallest mean squared error that was generated. We then just used a multi-layer perceptron, and then the really fancy stuff in time series now, recurrent neural networks, LSTMs as they're called. So it turns out it's not true. It turns out that, in fact, you don't beat linear regression with this stuff, but you do have the added benefit of run times that are 5-6 orders of magnitude more costly to engage in. So, as they say in finance, you come for the fees and you stay for the lousy performance. And so I do this kind of to get people to think about data generating processes and underlying ideas, and whether bringing a howitzer to a knife fight really, really works. And maybe it doesn't. But we talked a bit earlier about Bayes, and I think, in fact, deploying Bayesian techniques in this framework is actually a really interesting way to think about something from an economics perspective. So let's do a little bit of Bayes, and I think that this basically can allow us to examine something meaningful. So here, more lousy Python code written by me, non-deployable. This uses a package called PyMC3. I'm sure they've changed the syntax a bit, but you can take the basic linear model. You can say, what are my priors on the intercept or bias, the slope coefficient. I can take the data, The beauty of Bayes is that it's like this continuous process of bumping data against one's transparent beliefs. So in some lines of code here, I've stated what my beliefs are, and I've bumped my data against my beliefs to come up with a posterior. So what do the results look like when we do this? So remember, I talked about alpha, the basic conjecture that it's probably 0, should be 0 in an efficient market. This idea that beta, ideally, if we could do it, we could get it to be less than 1, so that we are not taking on more risk than the market. And so what I've done here is told it to graph this stuff out. I've put some red vertical lines against the posterior distributions. But now we can ask some interesting questions. We can basically say, what's the joint probability that alpha is greater than 1 while beta is less than 1? Right? This would be a real trading opportunity, a joint hypothesis that one could think about from a Bayesian perspective. In a frequentist perspective, that's a really difficult hypothesis to think about. In a Bayesian perspective, it's clean. We can write out everything very cleanly. So when I do this, basically if we go back to the graph, look at most of the mass for alpha lies above 0. A fair amount of the mass of beta lies below 1. And then we can easily calculate the joint probability, and it's 18.9%. So the probability that alpha is greater than 0 and beta is less than 1 jointly is, let's round it to 20%. When you're bumping a lot of money against a portfolio, these are really, really, really good odds. And you're starting to see lots of finance companies who have a lot of money trying to think about new and novel ways to think about data science and techniques to apply to it. And lots of them are running in the direction of deep learning, thinking that they can deploy these things in a way to count the number of cars in a Walmart parking lot, in a way to change up a portfolio. But here's a potentially simpler way that you sitting at your computer basically could say, those are pretty good odds. So as I say, I don't want to keep us from drinks. I don't want to keep us from slightly cooler air. And I'm happy to take questions.